For the last 40-50 years, the power of computers has been getting faster every sort of 2 years or 18 months or so. After 2 years, it's time to buy a new laptop because it's twice as fast. That law, Moore's law, which has been going for so long, is starting to come to an end. Computers are no longer getting faster. Transistors already are nanometers in scale, and over the next few years I would expect to see transistors get even smaller, down to the level of perhaps even 2 nanometers in feature size. At that point, we have to start to really consider some of the effects that quantum mechanics predicts can happen.
Classical computing is fantastic. It works very, very quickly, but it is sequential. It does one thing after another. Very much like a cooking recipe, you have to add things in the right order for it to work. We get used to using it every day, but essentially it's limited by the fact that it has to do one operation after another. It uses digital information, it uses ones and zeros, so the on and off states of a transistor, and that's really all it uses. The difference in the quantum world is we can actually start to do calculations in parallel. And the way that I visualize that is, you imagine you're sitting in the middle of the Earth. In the classical world, we point to the North Pole, that's our 1 of digital information, or the South Pole, that's our 0. And those are the only 2 states we encode information in. In the quantum world, you can imagine you're sitting anywhere on the surface of the Earth, which means you've got some fraction of the up state and some fraction of the down state. That basically means you've got 2 classical bits of information in that one quantum state. And the advantage of quantum computing is every time you add a quantum bit or a qubit, you basically double the number of states that you can access. Why is that useful? If you now perform a calculation, you perform a calculation in all those possible states at the same time, which means you're doing those calculations in parallel and all the information at the same time. So one of the ways to look at that is if you were to write a telephone number on a piece of paper, a classical computer starts through all the A's in the directory, the B's and the C's, and eventually it will find your answer. A quantum computer will look at the whole directory at once and tell you the answer almost instantaneously. People have looked at all the different algorithms that quantum computers can do, and any industry that has huge amounts of information, such as UPS, having drivers traveling across the world, trying to shorten their travel times and reduce their costs, that's a typical area. Drug design, so looking at how you can look at all the different drugs that are out there, how that matches to the DNA of the body so that you can actually target that for the audience. Looking for huge amounts of data that comes from space and telescopes, anything where you have huge data, and big data is really, the key to pretty much everything in information technology nowadays. They won't replace laptops. I guess the kind of utopic view we have is you have your quantum chip where all your difficult calculations go, your simulations and everything else, but you still have your classical computer, which is actually going to control the quantum chip and work alongside it.